Alright, in this video we're going to open with considering a interesting question. And you're like, Professor Bright, why are you doing this? Because you already know the answer and you're just going to tell us. And I'm like, well, we're still going to talk about it. So, here we go. Can we compute a volume of a solid D just by considering the boundary? Why might this be advantageous? Maybe pause the video, give it some thought, and then resume. Well, at least conceptually, the boundary could be easier to parameterize than the actual surface. And then when we talk about the surface, right, we have to talk about, well, each surface, it might be easier to parameterize each piece of the surface. So maybe that's easier, and then we have to worry about normal vectors for the entire surface and orientation, all that stuff. Maybe it's just easier to look at the boundary. That's the idea. Okay, so if we assume that Gauss's theorem applies, here's what we know. Okay, this is just using some previous knowledge. If we're thinking about volume, right, we know that the triple integral over the solid and then 1 dV, that's the volume of region D, of that solid D, right? And we also know Stokes, or Gauss's theorem, sorry. Actually, let me do that differently. Go away. So double integral over closed region, the boundary of D, f dot ds is equal to the triple integral over the over D, and then of the divergence. Okay, we know that. And now really what we want, if we're looking at these closely, we want this to be the same as that. So what we really want is the divergence to be 1. Okay, well, how do we make that happen? Well, big thing is force it. And so this is what mathematicians do sometimes. So we might want to choose convenient vector fields. So maybe we want to choose, I don't know, x0, 0. Okay, something that when we do the divergence of it, it's 1. Or similarly, 0, y, 0. Okay, we could also do something like x by 3, y by 3, z by 3. We could do something like x, x, x. Okay, so in these scenarios, if we can recognize that the divergence is 1, then we're just going to get the volume. Okay, and all we had to do is consider the boundary. So that's interesting. So this example, it's also interesting. Okay, so if we look at this thing and we want to compute the volume of the region, okay, so we can do triple integral. Okay, we know this is going to be triple integral of 1 dV over region D. Okay, so it's kind of an interesting figure. It's kind of if you think of taking a cylinder and punching both ends into the middle such that they meet in the middle, so this actually slopes down in the two ends. Let me draw it a little differently. Let me use maybe purple. All this would slope down into here, and all this would slope up into here. That's kind of what it looks like on the interior. So this is going to be perhaps fun. I don't know. Maybe, maybe not. Okay. If I want to compute this, that's really what I want, but instead I'm going to use Gauss's theorem in the other direction. So I'm going to look at the double integral over a closed region of the boundary using the parameterization. Okay, f dot ds. Okay, well, to do this, okay, this is where the process can get a little lengthy. You need to find your tangent vectors. Okay, so this ends up being minus sine u cosine v, and then negative sine u sine v, 2 cosine 2u, okay, and then tv is let's see. So this is going to be minus cosine of u sine v, and then cosine u cosine v, and then 0, okay? And then we're going to have to cross them, okay, to get this normal vector. Okay, tu cross tv is equal to, and now, oh boy, minus 2 cosine u cosine 2u cosine v. That's just the first component. Minus 2 cosine u cosine 2u sine v, comma, minus sine u cosine u. Okay, now the only thing that we have to be careful of is that we wanted outward pointing normal vectors, and I believe that this, if you look at it, it would actually point inwards. So this is, we would need to change, we would just need to acknowledge that this is in the wrong direction and use the opposite. Okay, so then now the whole thing of this is that we need f dot ds, or we want this to be true, but remember we need f dot, or we need the del operator, and if this is 1, then we need to choose a convenient vector field. So the vector field that I'm going to choose, it can be any vector field as long as the divergence is 1. We're going to choose f as 0, 0, z. Okay, and when I do that, and do the composition. Okay, so let's maybe, I'm getting ahead of myself. So now, again, we're still saying triple integral of 1 dv is equal to the integral over the boundary of d that is closed, and then f dot ds. Okay, and when I do the composition, so I would need to do, okay, I'll figure out the bounds in a minute. I would have 0, 0, and then the z component was sine of 2u. And then I dot this with that whole stuff. Mainly, I mean, the x and y components are going to dot to 0, so I really only really care about the last part, which is sine of u cosine of u, accounting for that negative or that opposite direction. Okay, and then du, dv, and I need to figure out these. It happens to give me the bounds earlier on, so this is going to be negative pi by 2, and 0 to 2 pi. Okay, then after you do the dot product and the ensuing algebra, we end up getting pi over 2, or pi squared over 2. Okay, so highlights here, really not the calculation. It's more of, if we recognize that we want the volume, we need that divergence to be 1. So then after, and going through the algebra, this right here was kind of the key step. We had to choose f in a convenient way such that the divergence of f was 1. And this one, we could have chosen different ones. This one happened to make our life easy. All right, so maybe a useful strategy as we're working through group work and as you're working through the test.